Hi students, welcome in chemistry classes. I am Priyanka Jain and you are watching the videos of analytical chemistry. As you know, every Saturday I open a video in the English and at Tuesday we will see the video of Hindi. Okay, so that Hindi and the English both viewers can see the videos here. Alright, so today is analytical chemistry turn and here the video is on ion exchange chromatography. Okay, in our last lectures we have studied about paper chromatography, column chromatography and different types of separation techniques we have seen, right? And ion exchange chromatography is one of the very important technique. As you know, you have studied, whenever you have studied lanthanides and actinides, you have studied about the ion exchange chromatography, where we use this technique for the separation of lanthanides. Okay, so as from the name, you can see here, what is the name? Ion exchange chromatography. It means chromatographic technique where the separation is done with the help of exchange of ions is called the ion exchange chromatography, because here the separation of the sample components is taking place with the help of ion exchange. Okay, so here we can use it for the separation of proteins. Okay, this technique basically is used for separation of charged particles like proteins. Okay, now see here, as you know, in every chromatographic technique there are a stationary phase and there is a mobile phase. So first of all, see here, what is our stationary phase? In ion exchange chromatography, the stationary phase is a cross-linked polymer. Okay, this is a cross-linked polymer resin. Like this, generally in most general cases we use divinyl benzene cross-linked polystyrene. Actually, what happens on this polystyrene resin, there are covalently attached functional group. Okay, on the surface of resin, different types of ionic functional groups are present. So common ion exchange resins you can see here. One is strong acid cation exchanger, and this will have like sulfonic acid group attached to it. Another type of the resin may be weak acid cation exchanger. These are like carboxylic acid. This will have actually the carboxylic acid type of groups on their surface. Third may be strong base anion exchanger. Actually, cation exchangers will exchange the cations and anion exchangers will exchange anions. Here, the quaternary amines are present at the group. And the last type may be weak base anion exchanger. These will have amines as their group. Okay. Alright, now we know about the ion exchange reagents. These ion exchange reagents are incorporated in the HPLC column. Okay, we will use here HPLC type of columns. About the HPLC chromatography, I will talk you in another video. But understand here, in ion exchange chromatography, we use HPLC column. Okay, and in this column, what we are using? We are either using the micro-sized porous polymers. We can directly take their beads, these polymer beads we can pack here. Okay, we can take micro-sized porous polymer beads, or in place of it we can take porous silica particles. These silica particles that we are taking is porous. Okay, so this is coated with, this whole porous particles are now coated with the polymer. So we can use in both the ways. Either we can take porous silica particles and then we can do the coating of the resin, or we can directly take micro-sized polymer particles, beads. Okay, so what happening here, when we are taking this, then what is happening in our sample? Suppose in our sample the monovalent cations are present. Okay, M plus ions are present, and we are taking a strong acid exchange resin in which SO3H groups are present. These groups are present on the solid resin. Okay, and this M plus ions is present in our sample solution. When we are pouring it, what will happen? These ions will get attached at it. So what will happen? A bond is formed between this and this M plus. Okay, so now these M plus ions are get stuck on the solid surface and this H plus ions comes in the aqueous phase. Okay, this whole thing can be understood with the help of the instrumentation. So we are seeing here now what is the instrumentation. Before seeing the instrumentation, one more thing that you should know, what is mobile phase. We now know about the stationary phase. Now we should know about the mobile phase. Actually, in the ion exchange chromatography, the mobile phase is aqueous buffer solution. We are taking the aqueous buffer solution and the whole process. The retention time of whole the process depends upon its pH and its ionic composition. Okay, let's comes to the instrumentation. Okay, see here the instrumentation I have already made. You can see here in the instrument you can see there is a chromatographic column. This is our chromatographic column. So first thing that we have to do is what? We have to pack this column with the ion exchange resin in such a way that there is no air present in the ion exchange layer. Okay. So before this process, we have to pack this with the ion exchange resin. You can see here there is plus sign. It means we have taken the cationic ion exchanger. Or we can also take the anion exchanger where we will use minus sign, right? Before the procedure of the ion exchanger should convert it into a definite ion exchanger form. Okay, before the procedure starts, we should convert it to a definite ion exchanger form. It means if we are taking the cation exchanger, if we are using cation exchanger, then it should be charged with H plus ions. Or if we are taking anion exchanger, then it should be charged with OH minus ions. How this can be done? For this, what we are doing? We are passing a definite amount of acid or base through the solution. Okay, through this column, we are passing the definite amount of acid or base. Excess of acid or base is then washed with the water. It means, firstly, in this column, we are packing the cation or anion exchanger. Then we are charging it with H plus or OH minus ions by passing acid or base through it. We are passing acid or base. Now there may be excess of acid or base. So what we are doing? Then we are passing here water. We are washing this whole system with the water. Okay. Or another element we can take so that the unretained species can be removed. Some of the species get stuck here. Some of the species will not be stuck, will not react. Okay. These are called unretained species. So when we are passing water, these unretained species will go out. Okay. And our ions get adsorbed on the ion exchanger. Now these can be eluted with the help of suitable solvent. Okay. So in last we have to do the elution so that all the sample components can be separated. Now see what are the factors affecting the separation. The first factor is cross-linking. Cross-linking in the resin. Cross-linking is very much important in the ion exchanger resins because it affects the swelling and the strength of the resin. Okay, as the cross-linking will decrease, as the cross-linking of the resins decreases, what will happen? The rate of swelling will increase. Okay, so as the cross-linking goes down, swelling will increase. So we will have to use the highly cross-linked polymer. So divinyl benzene is most commonly used. This divinyl benzene is actually used as the cross-linking agent. This will create highly cross-linking in the resins. Another important factor, the next factor for the separation is the size of the particles. Size. We should see the size. For effective separation, we should take the fine and uniform particles. Okay. Hydrated ions with small radius and a greater charge have high distribution coefficient. So, hydrated ions with small radius we should use. An order of selectivity for typical strong acid cation exchange resin is if we are taking higher charge, suppose Al plus 3, this will have higher rate of selectivity. Okay, then Ba plus 2, then Pb plus 2. As the size is increasing, as the charge is decreasing, this selectivity for the separation will decrease. Okay, so higher the charge, smaller the size, easily it can be separated. It will have high resolution. So in this way, as the size is increasing, as the charge is decreasing, the rate of separation, the selectivity for the separation is decreasing. This will be in this manner. K plus ions are larger in size, Na plus is higher in charge. So this will be the rate for their exchange. Highly charged ions bind more strongly than the ions of lower charge. Similarly, within a group of ions of similar charge, those with the smaller hydrated radius binds more strongly. So, for a strong base anion exchanger resin, the order will be, if we are taking a base exchanger reagent, then the order will be like this. Always remember, charge should be higher and side should be small, like this. Okay. Third point is area. If we increase the area of the surface, if the surface area is increased, then it will improve the condition of attainment of equilibrium. Then the equilibrium can easily be attained. Okay, so the separation will be more clear. So more the surface area, more will be the separation. Next point, maybe for good separation, the solution should be passed slowly. Okay, the solution should be passed slowly. Next point is temperature. Temperature also affect the attainment of the equilibrium. A rise in temperature. If the temperature is higher, then separation will be more effective. So we should take a higher temperature. And next thing is the length of the column. Short columns are used for separation of anions. If we are taking the short columns, then it will be better for the separation of anions. And if we are taking a longer column, then it will be better for the separation of cations. Now there are two important terms that you should know. Okay, one term is thermodynamic exchange capacity. What is it? Number of ions adsorbed by a layer of ion exchanger 20 centimeter high and 1 centimeter square in cross section at the rate of migration of 0.5 decimeter square per hour. Okay, this is called the thermodynamic exchange capacity. It means the number of ions that are being adsorbed by a layer of ion exchanger resin. The layer of the ion exchanger resin should be 20 centimeter high and 1 centimeter square in cross section, and the migration is being done at the rate of 0.5 decimeter square per hour. It means the ions are passing 0.5 decimeter square in 1 hour. Then the number of ions absorbed by this layer is called the thermodynamic exchange capacity. Next one that you will see here is the static exchange capacity. Static exchange capacity means number of milligrams equivalent of the ions absorbed per certain centimeter per certain time interval by 1 gram of dry ion exchanger. Means number of milligram equivalents of the ions that are being adsorbed by the ion exchanger in a certain time interval, and our ion exchanger should be 1 gram in weight. We are taking here dry ion exchanger that is 1 gram in weight, and we are passing the sample with a time of certain interval. Okay, and then the number of milligrams equivalent that are being adsorbed will be called the static exchange capacity. Okay, now there are some formulas that you should remember. One important formula here is distribution coefficient. Distribution coefficient D is equal to CR upon CS M upon V. Here CR and CS are equilibrium concentration of ions in respective phase. M is here the mass of the exchanger, and V is called the volume of aqueous phase in centimeter cube. Okay, so here from this formula you can find out the static exchange capacity. Actually this CR upon D is called the static exchange capacity. So if you have asked about the static exchange capacity, then you can use this formula and you can find out the value of CR upon D, and then this will be the static exchange capacity. Alright, now we see the applications of the ion exchange chromatography. Ion exchange chromatography is one of the very important techniques, and you know this technique is basically used for the separation of lanthanides, because lanthanides are same in the all characters, same, they have same chemical properties and almost same physical properties. They differentiate in the size. So on the basis of the difference in the size, they can be separated out by an ion exchange chromatography. This whole thing I have told you in our lecture of lanthanides and actinides. If you want, you can see that lecture. The link of the lecture you will get in our description box. Okay. The next of the applications are determination of sodium and potassium in the mixture. So we can use this technique for the separation of Na plus and K plus ions. Actually what we are taking? We are taking here a column. For this purpose we will take a column, and this column is filled with the sulfonic acid resin. Okay, we will pack this with sulfonic acid resin. It means there are SO3H groups present, right? Okay, now we will saturate this whole resin is now saturated with H plus ions. Okay, and then the column is eluted with a solution of 0.7 mScl. This solution is used as eluent. This will be our eluent. Okay, so firstly we have packed the column with sulfonic acid resin. Then we will saturate it with H plus ions, and then the elution is done with 0.7 mScl. The sodium ions, these sodium ions are less strongly held. Okay, this will be less strongly held, so they will be come firstly from the column, and they are collected before the K plus ions, and then K plus ions can be collected. So the both Na plus and K plus are separated out. The solution can be then evaporated for the dryness, and our alkali chlorides we can wait. Okay. The next is the separation of amphoteric metals from the non-amphoteric metals. This can be easily done with the ion exchange chromatography. When we have given the non-amphoteric metals are like Fe, Cu, these all are non-amphoteric, okay? And we have given the amphoteric metals. Suppose amphoteric metals are zinc, tin or aluminium. So we can separate them by the use of a column that is packed with the cation exchange resin like SO3H, and then we have to wash it with the alkali solution. Okay, we are also here taking a column that is packed with the cation exchange resin. Okay, and then the elution is done with the alkali solution. Similarly, the separation of metals, alloys, high alloy steels can be done on the basis of the difference in the stability of the complexes. Okay, so firstly here we have to make the complexes of them. Addition of HCl. Suppose we have given Cu plus 2, Cd plus 2, zinc plus 2, Pb plus 2 and bismuth plus 2. These ions we have given, okay, and we are adding HCl to them. Okay, we are adding HCl to them. So what will happen? They will convert to their complexes. We are getting CuCl4 minus 2, ZnCl4 minus 2, okay, CdCl4 minus 2, PbCl3 minus and BiCl4 minus. Okay, so these complexes are formed. Now their stability will be in the different order. The stability is increasing from here to here. This is less stable, this is more, and this is more. Okay, so bismuth complex is most stable. Now the solution is percolated through the column. This whole solution of these complexes we are passing through the column. Okay, these are the complexes that are present in our solution, and we are passing them through the column that is packed with the anion exchange resin. So these whole complexes will get attached on this anion exchange resin, and then these metals can be eluted by the use of the elution is done with the help of dilute HCl, water and nitric acid. Okay, when we are using the 2NaCl, 2NaCl when we use, then this Cl will get separated out. And when we use 6NaCl, when we are using 6NaCl, then this zinc complex gets separated out. Okay, when we use 0.3 NaCl, then this cadmium complex gets separated out. And when we use water, then this lead complex gets separated out. And when we use the HNO3, then this bismuth will get separated out. In this way, the whole of the complexes will get separated out. Okay, so this is whole about the ion exchange chromatography. In more details, you does not need to know everything. This is whole thing that you should know, and I think this video is sufficient for you. Okay, and I hope you will like this video. Meet you in the next video. The next video will be on HPLC, high performance liquid chromatography. Okay, I hope you will like this video, and if you are liking, please comment me. Please share the videos and please comment me. Please like so that we can make more and more videos. Okay, thank you.